Okay, we're back with another question, another induction question. This time it's a sigma notation question. A lot of people find these harder, but actually there's many tricks to this, and we'll make it simple for you guys. Okay, so first of all, this is the question. It's the sum of from r equals to 1 to n of the index r times r factorial. R factorial is just r times r minus 1 all the way down to 1 is equal to n plus 1 factorial minus 1. So some people get confused about the index. So here r is an index, so essentially like it's increments every time. What this would be 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial all the way to n times n factorial. And we're saying that this is equal to n plus 1 factorial minus 1. This is just a demonstration of how this works. Okay, so now we want to prove this, right? So first, we always write, in this case I'm just going to write let Pn, the proposition, I don't have space right here, the proposition be this, okay? Copy that down on the page in the exam test. So first, we always start with the base case. So first, let's consider the base case P1, all positive integers, those are the main. So what we do is we basically just sub it in here and show that it's equal. So what we do is that the left hand side is equal to sum of r equals 1 to 1, so that's just summing 1. 1 times 1 factorial, that's just one index, so it's just equal to 1. What it is here is right hand side is equal to 1 plus 1 factorial minus 1. What's 1 plus 1 factorial? 2 factorial, that's 2 times 1 minus 1. This is equal to 1. Left hand side is equal to right hand side. Thus, the base case holds true. Okay, what we do next is we first, just for the sake of like making sure that you know what you're trying to prove in the exam, we always recommend you to write down what you're actually trying to show. So, first, actually, what we actually recommend you to do is to assume that if Pn holds for a case n equals k, which is just any positive integer. And so what we do is that assume pk holds true. And the point of induction is that you want to show that pk plus 1 will hold true when you assume pk holds true. So we want to prove, that sum of n plus 1, we're changing the n's, don't be confused. Oh wait, sorry, that was well, it still works. I guess putting k is better. So we want to prove that the sum, the k plus 1, just always remember, don't confuse yourself with the index. You see an n, you sub it where n is. Okay, you always sub it where k plus 1 is into n. Note that, okay? And then r equals 1, and this is also the same. Okay, what about here? We see an n plus 1 here. We see an n here. So what we do is that we do k plus 1, and then plus another 1, because here. Factorial minus 1. We want to show that this holds true. So assuming pk holds true, we want to show this. So by the induction, by just definition of what a sigma is, r equals 1, k plus 1, and this is equal to actually the sigma of k, r equals 1, of k and k factorial. And then since it's sigma, right, if you rotate it up to the kth case, then I want the k plus 1. K plus 1 is k plus 1 factorial. Okay, by our induction hypothesis, we assume that pk holds true. So this holds for for a case that where n equals k. We can write this. Use our assumption. We can write that k plus 1 factorial minus 1 plus k plus 1 multiplied by k plus 1 factorial. Okay, just to make this less confusing, I'll put a bracket here and a bracket here. With that, you see there's a factor of k plus 1 here. Let's group them together, make it more obvious for ourselves. This is equal to k plus 1. From here, this is just, because they're all adding up to each other, right? You can shift them wherever you want. K plus 1 factorial plus k plus 1 factorial minus 1. Okay, this is the same as that. This is a factor of k plus 1, this is a factor of k plus 1 factorial. Both has a factor of k plus 1 factorial, that's what I'm trying to say. So what we do is that we take out a factor of k plus 1 factorial, and we factorize this, so it becomes k plus 1 from here. And here, how many k plus 1 factorials do we have? We have 1. And then we have to put back the minus 1. Okay, so simplifying this, k plus 1 plus 1 is just k plus 2. And k plus 2 multiplied by k plus 1 factorial is equal to k plus 2 factorial minus, and then minus the 1 at the back. And we see, we've shown that this holds true because when we simplify this, so I didn't do it just before, it's just this. So we're not done yet. Always remember to write your conclusion because those are free marks right there. So what I want to say is that since P1 is true and PK holds true, PK plus 1 holds true, sorry, when we assume PK is true, thus Pn holds true for the whole domain, for n all the positive integers. And we're done. Yeah.